All right, thank you all for coming to our latest installment of the High Energy Lunch Seminar. Today's first speaker will be Lauranne Lanz, who will be talking about constraining AGN structure using reflection and reprocessing in SwiftBat AGN. Lauranne holds a Bachelor in Physics and Astronomy from the University of Maryland, College Park, and a PhD in Astronomy and Astrophysics from Harvard. She worked with Christine Jones and Bill Foreman on radio galaxies and completed her thesis with Howard Smith and Matt Ashby, focusing on galaxy mergers. Her postdoctoral research at IPAC with Patrick Ogle focused on star formation activity in radio galaxies. And in her second postdoc at Dartmouth, working with Ryan Hickox, she focused on AGN activity in post-starburst and SwiftBat galaxies. Her talk today will discuss one of these projects. And as of fall 2019, she's an assistant professor at the College of New Jersey. So thank you, Lauranne.
Thank you. So yes, so today I'm going to be telling you a project that I did with Ryan when I was a postdoc at Dartmouth. This is work that also involves good collaboration with Mislav Bolokovic, Taro Shimizu, Claudia Ricci, and Andy Golding. In 20 minutes, I don't have time to go through all of the nitty-gritty details of all of the little things that we did in this project, but here's the reference if you want to go and have a read at a later date. And I'm always happy to talk about this project in more detail. So let me start by motivating this a little bit by talking about the big picture question that we wanted to address, and that's really whether AGN are all structured the same. We're all familiar with the cartoon of the AGN as a donut, which has a typical covering fraction. And then depending on our viewing angle, we end up seeing it as a type 1 or type 2. But increasingly, I think we're coming to a consensus that AGN are much more like a bakery shop. There's great diversity in all of this. And so there's likely to be a large variety in covering fraction distributions. So what this project really set out to do is seeing what constraints can we put on the distribution of covering fractions? And we decided to address this question using SwiftBat AGN and specifically focusing on low redshift AGN at redshifts less than 0.05. And we removed any beamed sources from the set. So in the 58-month catalog, that gave us 416 sources. And we wanted to use a combination of infrared and X-ray to probe this question. So that limited our sample fervor to the 313 AGN looked at by Taro Shimizu and Melendez in that collaboration. They had taken Herschel observations of SwiftBat AGN, 313 of them, and had combined that data with WISE observations. And then in the 2017 paper, Taro had fit these observations with this kind of model comprised of an exponentially cut off power law for the AGN and a modified black body for the star formation component. And so this let them determine high fidelity infrared luminosities for all of these AGN. We then cross-correlated this set of AGN with the 95 Seyfert-2 AGN, all SwiftBat galaxies, from the 70-month catalog that Mislav had looked at with NuStar. And he had combined those observations with Swift XRT data and undertaken phenomenological modeling of these spectra, which gave us, amongst other things, observed intrinsic and reflected X-ray luminosities in 2 to 10 keV, 10 to 50 keV, as well as obscuration column, Peck-Srev reflection parameter, power law indices, all of the good things that you would want out of X-ray spectra. Now, not all AGN had both of these. So when we cross-correlated, we ended up with 69 AGN, which is the set of galaxies that I used for this project. One good thing, though, is when we looked at the distribution of luminosity and redshift, we find that our set of 69 is relatively consistent with all of the parent populations, including the low redshift BAT AGN, suggesting that these results are likely applicable to more than just the 60N AGN. So we have infrared luminosity, we have X-ray luminosity. What do we like to do when we have multiple luminosities? We plot them against one another to see what kinds of correlations we can find. Unsurprisingly, all of these galaxies pretty much agree with the intrinsic X-ray to infrared luminosity correlations. The colored lines here are various literature relations. The black line is the fit that I got to these data. This is pretty much consistent with what we see. But we also see a correlation between the reflected X-ray luminosity and the infrared luminosity. And to test the strength of these correlations, we undertook an ASERF survival analysis to do this. And the reason we did that is because if you see all of these triangles, those are upper limits. And by using survival analyses, we can include that kind of information in determining our correlation. We determined the Spearman-Rowe rank correlation parameter, which has an associated probability of whether or not we can reject the absence of a monotonic correlation. Is it statistical language fun? It's not just can we confirm a correlation, it's can we reject the absence of a correlation. So if the probability is less than 10 to the negative 3, then we reject the absence of a correlation. And so what you can see is that both the intrinsic and the reflected X-ray luminosities appear to be correlated with the infrared luminosity. To determine how much we trust these correlations, we undertook a bootstrapping analysis where we would pick samples out of these sets of observations and with replacement and then rerun the analysis. There's a little bit of a bear to put these two things together. So if you are interested in doing this kind of analysis, I encourage you to start with the code that I've made available on GitHub because it was not necessarily all that fun to put together. So if you can avoid reinventing the wheel, please do so. So we find, though, interestingly, that the correlation with reflected X-ray luminosity appears to be at least slightly stronger than the correlation with intrinsic X-ray luminosity. Now, I cannot say that this difference is statistically significant. Our sample size appears too small to make that claim, but it is interesting that there is a somewhat stronger correlation with reflected luminosity. What this might mean is that in this picture, where the torus is doing both kinds of processing, the reflection of X-rays and the absorption of UV and optical light, transforming it into infrared, there may be a similar distribution of the material that's doing the reflection and the reprocessing, even if it's not exactly the same material. And both of this material is likely to be located in a region that we call the torus. So if we look at the work of Stefan or Lusso and Risalti from the mid-2000s, they showed that there was a tight correlation between the UV and optical emission of the accretion disk and the coronal X-ray emission. So the fact that we're finding a good correlation between reflection and infrared suggests that you would also want the material doing the reprocessing to be somewhat correlated to avoid reducing that level of correlation. We might also expect that the degree of reprocessing, whether it's in reflection or in infrared, would increase as our covering fraction increases, because just if there's more of your sky that's covered by this material, you would expect that it would capture a greater fraction of the intrinsic emission and transform it. So we're going to use this assumption that the degree of reprocessing depends on the covering fraction to probe the covering fraction distribution. Now, we're not going to make any sort of explicit assumption about the distribution of that material within the torus. So our analysis doesn't actually let us say anything about the degree of clumpiness or the structure of the torus. It really just lets us probe the distribution of covering fractions. So we want to use this relationship between reflection and infrared to probe this question. But luminosity may not be the best frame to do this in, since it encodes things like mass accretion rate. So what we decided to do was divide both axes by intrinsic X-ray emission. But while we were doing that directly for the y-axis, for the x-axis, we took an additional step. We used the intrinsic X-ray emission to calculate the expected infrared emission using the Chen et al. Relation. And that is what we end up dividing the x-axis with. So we have the observed infrared divided by the expectation based on the intrinsic X-ray emission. Another name for the y-axis is the Pexrav reflection parameter, and we're going to call the x-axis the infrared axis. All right, so now we have the observables that we want to use to test our covering fraction distribution, and our approach is going to be forward modeling. We're going to generate these observables for a variety of covering distributions and see which ones have observables that are consistent with our actual sources. So to do that, I start by generating a distribution of 10,000 covering fractions for AGN. This is an approximately uniform distribution going all the way from completely covered to completely uncovered. But if you remember way back at the start of my talk, I mentioned that the set of sources that Mislav was working with were all Seyfert-2 galaxies. And those are type 2 galaxies. And if I compare all AGN to type 2, that's not really an apples to apples comparison. So I'm going to want to select the subset of these AGN that would be identified as type 2. And I do that by relying on the work of Moshe Litzer and Hagai Netzer to make the assumption that the probability of being observed as type 2 increases as the covering fraction increases. So based on this assumption, I probabilistically select the subset of my 10,000 AGN that would be observed as type 2. And unsurprisingly, I get about half of them, about 5,000, with a definite skew towards higher covering fractions. Great, so now I have covering fractions. I want to then convert these to my observables. And I do that by using a relationship that Mislav discussed in his thesis between covering fraction and Pexrav reflection parameter based on more complex modeling that he did of X-ray spectra. And then for the infrared excess, I rely on the fact that the Chen et al. Relation is specifically calibrated based on type 1 AGN. So we assumed that the degree of reprocessing depends on the covering fraction. The greater the covering fraction, the more reprocessing into infrared. So to calculate IR excess, I divide the covering fraction of my type 2 AGN by the average covering fraction of all of my type 1 AGN that were not selected, since that is where the expectation of the infrared luminosity would come from. So this gives me a way of calculating both observables based just on the covering fraction distributions. And so I did this for all 5,000, and that gives me the red contours. So now the next step is to ask, are the red contours and the blue dots, which are my observed sources, consistent with one another in terms of their distribution in 2 dimensions? To do this, I use a 2-dimensional KS test. The formalism comes from work done by Peacock in 1983. Andy Goulding had codified it in 2014, and then I adapted this code for my specific needs. Now, the 2-dimensional KS test is not quite a run it once, you'll get an answer, it'll be great. There is some uncertainty in there, so we ended up having to do bootstrapping to pick out samples from real and mock data and run the test on each. We did that 10,000 times, and that ends up giving us this distribution of 2-dimensional probabilities. If the probability is less than 10 to the negative 3, we reject the idea that the hypothesis that they come from the same parent population. If it is above 10 to the negative 3, we don't reject it. So the black line shows you where 10 to the negative 3 is. The red line shows you the median of this distribution along with the typical width of the distribution, which gives you a sense of how much we trust the median. So this was our methodology going forward. We run all of these bootstrapping analyses, we run all of these models, and we want to test a variety of models to get a sense of what kinds of distributions are consistent with our observations and not. So we did wide models, we did narrow models, models skewed to low covering fractions, models skewed to high covering fractions. We ended up looking at 421 different variations on a theme. 420 were Gaussian models. This was selected just to have some degree of similarity. And then to that, we added up a uniform model. So for each of these 421 models, we generate a distribution of 10,000 sources. We pick out the type 2 AGN probabilistically. We calculate the observables. Some of them clearly don't agree. Some of them are a bit iffy, and some of them agree decently well. Then we run our KS analysis, and we use 3 kinds of color coding. So galaxies in blue are galaxies where the median of the probability is greater than 10 to the negative 3. So this is a model where the observables are consistent with our observations. In red, we have models where the distribution's median is well below 10 to the minus 3. This is a model that we can robustly reject. And then we have the in-between cases, which are in purple, which is where the median is less than 10 to the negative 3, but the uncertainty on that median extends above 10 to the negative 3. So while we are most likely going to be rejecting this model, it is plausibly consistent with the null hypothesis, so we don't want to completely rule it out. All right, so this is the plot in which we are going to look at all of our models. We're going to use these color scales that I just described. On the x-axis, you have the mean covering fractions, and on the y-axis, you have the width of the distributions. So in the lower left, narrow skewed to low covering fractions, upper left, wide skewed to small covering fractions, in the upper right, wide, high covering fractions, and in the lower right, narrow skewed to low covering fractions. And each model is going to get a square colored according to whether or not we accept it or not. So these are the 4 models that we looked at before, and this is the set of 421. This analysis cannot tell you this is the one and only true model, this is the correct answer. But what it can show you is tendencies in covering models that will agree with the data and ones that we can reject. So for example, we can tell that narrow models, particularly those that are skewed to low covering fractions, just do not agree with our data. And skewed to low covering fractions, even when they're broad, that just doesn't work compared to our data. What we can also see is that regardless of width, models that center around 70 to 80% as the average covering fraction tend to do pretty well. And we can also see that broad covering fraction distributions tend to have a wider range of centers that will give us observables that agree with our data. One other thing that we can see is that once you get above a full width half max of about 1, increasing the breadth further doesn't seem to do much in terms of increasing the number or the types of models that will agree with our data. We also see that a uniform distribution is consistent with our observations. So how do these results compare to other efforts to constrain the covering fraction distributions? Well, this has generally been done one of 2 ways. So for example, Cristina Ramos Almeida and Claudio Ricci, amongst others, have used the distribution of column density as a proxy for covering fraction distributions. And they find that based on X-ray observations, you would tend to expect that the typical covering fraction of a BAT AGN is around 70%. Silvia Mateos, and amongst many others, has used detailed clumpy torus modeling of infrared SEDs to constrain covering fraction distributions. And when they do that, the typical result is that they want to have broad distributions of covering fractions. And so I find it really neat that our approach that used both X-ray and infrared found results that are consistent in both. We also like broad distributions. We also like them to be centered around 70%. So this was essentially what my project showed, but since I do have like maybe a minute or so, let me just briefly advertise a second talk that I will be coming to give at some point in the spring in the Galaxies and Cosmology seminar, which also uses a forward modeling approach, but in this case looks at post-starburst galaxies, where we have 12 of them with between 3 and 10 photons in the 9 that we detect, and it's really only with forward modeling, with generating lots of models, that we are able to get useful information about these sorts of things. So to come back to what I discussed in this project, we think that the correlation between reflected X-ray luminosity and infrared luminosity tells us that it's likely to be a common reprocessor, or at least a related one that's distributed in a similar way. And a relatively simple empirical model is able to reproduce this relation, generally with a broad distribution or one centering around a typical covering fraction of 70%. Thank you.
All right, thank you, Lauranne. Fantastic work. Do we have any questions? If you would like to ask a question, please either raise your hand or send a message in the chat.
Was I just incredibly clear?
All right, we have a question from Aneta. Did you use the errors in the correlation analysis?
It's a great question. Honestly, it was more than a year ago, so I don't completely remember, but it wouldn't entirely surprise me, but I'll double check Aneta and I'll let you know for sure. But that would also be available in the code as well.
We still have time for questions, so don't be shy. Okay, a question from Belinda. Over what wavelength range was the infrared luminosity correlated?
So it was the infrared luminosity from the SED fits. And those came out of SEDs that contained WISE and Herschel observations. I think they just, if I remember correctly, it was total infrared luminosity, but it wasn't at a specific wavelength like 12 micron. No, so it was corrected for star formation. In Taro's paper, they also looked at Herschel reference survey sources to get a sense of how much contamination the mid-infrared luminosity would have. And they used that to correct the mid-infrared luminosities for any star formation contamination. Sure.
All right, we have time for maybe one more.
Hi, Dr. Nice, very nice talk. May I ask a question?
Sure.
Who's this?
Yeah, Shuri. It's Shuri.
Shuri.
Hi. So is your conclusion of the current factor distribution apply to only Cepheid-2 galaxies? I mean, type 2 AGN, or it's applied to different types, all types of AGN?
I think it applies beyond type 2 because the underlying distribution, the yellow histograms, are for all AGN. And then out of those, I select the type 2 to do the comparison with.
Did you find a distribution difference between different types of AGN? For example, if type 2 AGN have a smaller current factor and the type 1 has larger one? Oh.
So let me just go back a little bit. Let me see. So I don't distinguish between type 1 and type 2 initially. So the yellow histogram of my 10,000 AGN would be for all of them. And then out of those, I select the subset probabilistically that would be type 2. So you can see that when when the distribution is skewed to low covering fractions, I end up selecting 20 to 40%. But when it's skewed to high covering fractions, I end up selecting mostly type 2 AGN. So well, what this would tend to say is that the covering fraction distributions of type 2 would tend to peak at a higher mean covering fraction, whereas the type 1 AGN would tend to peak at the low covering fraction, but that might be an artifact of the way that I'm doing this. That said, it is somewhat consistent with the work that Celia Mateos did, because the black line was their total AGN distribution. The red line was their type 2, the blue line was their type 1. I did digitize this distribution and run one analyses using that form for all of the AGN. And I ended up getting a probability that it agreed of 10 to the negative 3.5, which would put it in the purple category of this is still plausible as a distribution that would agree with my reflection infrared correlation.
Thank you very much.
Sure.
All right. With that, we should probably move on. Thank you again, Lauranne, for joining us and presenting your work.
Sure.
Thank you, Lauranne. So our second speaker today is Dr. Vivienne Baldassare. She is the William Band Distinguished Assistant Professor of Physics and Astronomy at Washington State University. She received her PhD from the University of Michigan in 2017, where she was working on the properties of active galactic nuclei in dwarf galaxies. And prior to her current position, she was an Einstein postdoctoral fellow at Yale University. So Vivienne, take it away.
Great, thank you for the introduction, and thanks for having me to present at the seminar today. So as Ruchi said, I'm currently at Washington State University as of August of this year. If you're not familiar with us, we are the other major state university in Washington, but on the complete other side of the state. So not near Seattle, but rather right up against the border with Idaho. And hopefully some of you will have a chance to visit sometime. It's been really nice living out here, really beautiful. All right. So I won't give much background on why we are interested in searching for massive black holes in dwarf galaxies, but I did want to note that they're important to find not just for understanding the full population of supermassive black holes and galaxies in our universe, but also because we think that the population of massive black holes in dwarf galaxies may be an important constraint on models of black hole formation and growth, among a myriad of other interesting topics, such as what does AGN feedback look like in dwarf galaxies? Can active galactic nuclei influence the evolution of dwarf galaxies in any way? And perhaps most importantly for some, dwarf galaxies are also a good place to search for intermediate mass black holes. So as I'm sure we're all familiar with, we generally see black holes at either masses of less than about 100 solar masses. These are stellar mass black holes, or the supermassive black holes that sit at the centers of galaxies, which tend to be maybe a million solar masses and up. And the search for intermediate mass black holes has been a very popular topic lately. The recent LIGO IMBH sits down here at about 150 solar masses. And then in dwarf galaxies, the kind of black holes that I'm interested in looking for are at the other end of this intermediate mass range, around 10,000 to 100,000 solar masses. And so based on scaling relations between black hole masses and galaxy masses, we expect to find these intermediate mass black holes in dwarf galaxies, which generally refer to galaxies with stellar masses less than about that of the Large Magellanic Cloud, a few times 10 to the 9 solar masses. So dwarf galaxies are a great place to search for intermediate mass black holes. And the population of black holes and dwarf galaxies is important for understanding AGN feedback, as well as black hole formation and growth over cosmic time. Unfortunately, it can be really tricky to detect massive black holes and dwarf galaxies. So for more massive systems with black holes of 10 to the 7, 10 to the 8 solar masses, we can, at least for the most nearby systems, do dynamical detection, look at the motions of stars or gas in the gravitational sphere of influence of the black hole. But for dwarf galaxies, this is largely not possible. Sometimes it can be difficult to even identify the dynamical center of a dwarf galaxy, which is the case for the Large Magellanic Cloud. And so generally we turn to searching for active galactic nuclei in dwarf galaxies. So we search for massive black holes in dwarf galaxies that are actively accreting, since those signatures are more easily detectable. There are also problems with the general AGN selection techniques that we use. So there are a lot of observational biases associated with using things like the BPT diagram and optical spectroscopic signatures to find AGN and dwarf galaxies, since low metallicity or star formation dilution can mean that you don't necessarily observe the typical narrow line signatures that you do for higher mass AGN. And so a lot of the work that I've been doing recently has been focused on trying to find other ways of detecting AGN in dwarf galaxies. And the area that I've chosen to focus on is using optical photometric variability to detect AGN in dwarf galaxies. So a nice property of AGN is that they vary on human timescales. So AGN typically show aperiodic flux variations at all wavelengths on a wide variety of timescales. The plot here on the right is just an example of particularly well-studied variable AGN, NGC 5548. And you can see that the flux output from this AGN varies by a factor of a few over the course of 8 years. And this variability is typically attributed to instabilities and turbulence in the AGN accretion disk. Since we are in the era of time domain astronomy right now, we have a lot of really nice repeat imaging surveys currently available, and the Vera Rubin Observatory, LSST, will be online soon. There's just a wealth of data that can be used to search for variable AGN in dwarf galaxies right now. So my goal has been to use this optical photometric variability to try to find AGN in low mass galaxies that might be missed by other selection techniques, such as the widely used BPT diagram. In the last couple of years, I've focused on 2 different surveys, Stripe 82 and the Palomar Transient Factory. And so what I did for these 2 data sets was to reprocess the available data and then search for variability in large samples of galaxies spanning a wide range in stellar masses, but with a focus on trying to detect low mass AGN. And just to run through some of the basic properties of these surveys that I carried out. Stripe 82 was a survey run by the Sloan Digital Sky Survey between 1998 and 2008, covers about a 300 square degree strip of sky. And the sample in which I searched for variability was comprised of 28,000 galaxies from the NASA Sloan Atlas, spanning from about 10 to the 7 to 10 to the 12 solar masses. The typical baseline for my reconstructed light curves was about 6 years with a median number of data points of 17. I also carried out a search using data from the Palomar Transient Factory, which was run from 2009 to 2017. This had a much wider area covered. In the map on the right, it shows the PTF sky coverage map, and it's color coded by number of observations taken. It's hard to read the label, but it goes from 0 to about 7,000 at the top end. So there's just a ton of great data in this data set. And the sample here was about 47,000 galaxies. And I chose here to focus on galaxies with stellar masses below about 10 to the 10 solar masses. So most of those galaxies are low mass. The baseline for these light curves ended up being slightly shorter, about 4 years, but with more data points per light curve with a median of 70. So between these two surveys, I searched for AGN variability in almost 50,000 low mass galaxies. In order to construct light curves, I used difference imaging analysis in order to try to detect a faintly varying AGN superposed on top of a host galaxy. You want to be able to subtract off the light from the host galaxy to detect these lower levels of variability. So the first step here would be to construct a template image from your best quality frames, your best seeing and lowest background, and then you basically degrade every other image. You degrade the template to match the seeing of each other image, subtract the two, and are left with a flat difference image, and then anything that's varying will pop out against the background there. I then would construct a light curve for each of these galaxies using forced photometry and an aperture of 2.5 arc seconds, chosen to be slightly larger than the worst quality seeing images that I used. So this is an example of a galaxy that was not found to be variable. You can see the Sloan image there on the right with the 2.5 arc second aperture, which was just centered on the position of the galaxy as given by the NASA Sloan Atlas. And this video shows the difference images. So here you can see that the background is just flat. And then for galaxies that were variable, we assessed whether they were varying in a way consistent with AGN by determining the goodness of fit to a damped random walk model, which is generally a good empirical descriptor of AGN variability. So the light curve here is shown on the bottom. It's the G-band magnitude versus time. The data points are given in gray, and then the blue shaded region shows the best fit damped random walk model, which in this case is not relevant since this galaxy isn't variable. And then this is an example of a galaxy that is variable and also well described by a damped random walk. Okay. So in the end, between the two surveys, I found about 300 or so variability selected low mass AGN. And here are a couple of examples of those galaxies. So the one on the left is the lowest mass galaxy that I found to have AGN-like variability. You can see in the light curve, it's variable and also consistent with the damped random walk. The one on the right is kind of a cute example because it has kind of a funky morphology in this off-center knot, which is the position of the variable source as well. So these are a couple of nice examples that had AGN-like variability. Since all of these galaxies have SDSS spectroscopy, I wanted to see where these variable AGN sit on the BPT diagram. So this is the BPT diagram, which, if you're not familiar, characterizes galaxies, characterizes the dominant source of photoionization in a galaxy as due to AGN, star formation, or a composite. So typically AGN will fall in that upper left region of the BPT diagram. And here I'm showing all of the variable galaxies from the PTF survey that had AGN-like variability, and they're color-coded by galaxy stellar mass. And so Interestingly, for the high mass galaxies, basically everything that has AGN-like variability is also a BPT AGN. But for the low mass galaxies, the vast majority of low mass galaxies with AGN-like variability fall in the star forming region of the BPT diagram. So would potentially be missed by typical AGN selection diagnostics. Right, so the variability selected AGN with star formation dominated narrow lines are AGN that are missed by this particular selection technique. I also wanted to explore the AGN fraction as a function of galaxy stellar mass. So that's what's shown on the left, variable AGN fraction versus stellar mass. The red shaded region is just where the galaxy sample was incomplete. Since I said for the PTF survey, I focused mostly on galaxies with stellar masses below a few times 10 to the 10 solar masses. But nevertheless, you can see that you have this rise in the variable AGN fraction towards higher stellar masses, which is also reflected in the histogram on the right, which shows the distribution of host galaxy stellar masses for the full sample in gray and for the variability selected AGN in blue. So at first glance, it appears that the variable AGN fraction is strongly dependent on galaxy stellar mass. But we also have to take into account the fact that the variable AGN fraction is also dependent on the apparent magnitude of the nucleus, which is to say that we can detect lower levels of variability in galaxies with brighter nuclei. And since the dwarf galaxies skew fainter compared to higher mass galaxies, we need to account for this difference in magnitude distributions if we want to compare the true fraction of variable AGN in different mass groups. Okay, so this represents my effort to control for the different magnitude distributions for high and low mass galaxies in this sample. So the histograms on the right show the magnitude distribution for high mass galaxies in gray, and for galaxies with stellar masses between 10 to the 9 and 10 to the 10 in the kind of orange-red color. And so what I did was to draw subsamples from that distribution that matched the magnitude distribution of the higher mass galaxies, and then compare the fraction of variability selected AGN in these magnitude matched subsamples. So the main takeaway here is that in high mass galaxies, the fraction of variability selected AGN is about 1.5%. And then for galaxies with stellar masses from 10 to the 9 to 10 to the 10 solar masses, once you control for different magnitude distributions, is about 1.4% plus or minus a few tenths of a percent. So consistent with the higher mass galaxies. Below 10 to the 9 solar masses, the fraction does appear to drop, but it's also important to note that we may not be sensitive to the black holes that would reside in these galaxies in terms of the depth of the observations, and Sloan is not complete at these galaxy masses, so that should be taken with a grain of salt. But these data do show that the fraction of variability selected AGN appears to be constant down to about 10 to the 9 solar masses, which suggests that probably the occupation fraction doesn't drop drastically down to about 10 to the 9 solar masses either. Okay, so in the last couple minutes here, one interesting question is, why are we missing most of these lower mass AGN with optical spectroscopy? It could be due to low galaxy metallicities, which can impact where an object falls on the BPT diagram, or star formation dilution. But looking at differences in galaxy properties between dwarf galaxies with BPT selected AGN and variability selected AGN can help illuminate why this might be. So this just shows the color distributions of BPT selected AGN and dwarf galaxies from the Rines et al. 2013 samples, that's in purple, and then the PTF variability selected AGN in the same stellar mass range in blue. So these objects skew towards bluer colors, which is suggestive of perhaps something like star formation dilution being the reason that these don't, these aren't selected by the BPT diagram. And one thing I'm really excited for is that this past cycle, I had a program approved, a joint Chandra HST program, to look at 9 of these variability selected low mass AGN with Chandra and HST to search for X-ray emission and characterize the host galaxies. So stay tuned for that. The data are just starting to roll in, and I'm really excited about this. So I think we're just about out of time. So I'll skip over this and just go to my takeaways here. Black holes and dwarf galaxies are really important for understanding black hole formation and growth, and are important in the search for intermediate mass black holes. These systems are traditionally elusive, but variability is a new and I think really promising way of detecting these black holes and dwarf galaxies, and is beginning to be able to place meaningful constraints on the low mass end of the active fraction and occupation fraction. And then there's, I didn't talk about this, but new surveys such as the Young Supernova experiment, which I'm a part of and I'm happy to talk about, which will be great for searching for fainter and lower mass AGN and dwarf galaxies. I'll leave it there. Thanks, everyone.
Thank you, Vivienne, for a great talk. If we have any questions, please raise your hand in the raise your hand feature or put it in the chat. There are a couple questions in the chat already, so I can read them out. I'm looking at the first one, actually. I'm not entirely sure if that's a question.
Thank you, Martin. I'll check that out.
Yeah. A second question from Aneta is, did you measure the black hole mass for these galaxies?
No, we don't, because they generally don't show broad emission lines, which might be related to the comment that Martin posted above. But one of the things that would be great is if you can find a strong relation between variability properties and black hole mass, then if you were to take higher cadence, more sensitive observations of these galaxies, then that might be able to give a clue into the black hole mass. But since they don't have broad emission lines, or at least not in their SDSS spectra, we don't have masses yet. Yes, from DRW. Yeah, so I think we probably just need better quality light curves, higher cadence to be able to do that. And that's something I'm working on pursuing.
Okay, I believe the next question was from Igor, who has a hand up. So please ask your question.
Hi, can you hear me?
Yes.
Yes, just to comment on this light curve stuff, you need like a resolution of minutes on IMBH to get the good sense of the mass. So it's like a dedicated project. But my question is actually about something different. You showed that most of them lay in the star forming sequence, along the star forming sequence in the BPT. Did you consider possibility that in fact you're not seeing the black hole, but rather some luminous blue variables or stuff related to massive stars? Like, you know, they're all variable. If you go to extremely luminous stars, they're all variable. So have you checked for the presence of, let's say, Wolf-Rayet features in the spectra?
Yes, so the spectra don't contain Wolf-Rayet features. There was one very nearby galaxy that we found to be variable, and this is work that I published with Colin Burke earlier this year. was an extremely nearby, very low metallicity dwarf galaxy that had some variability. But this galaxy also had some really strange features in its spectrum, P Cygni profiles and things like that. And so in that case, we were able to interpret that as a long-lived supernova or stellar transient. So definitely you can have some stellar contamination, but I think that generally that's only going to be an issue for the most nearby dwarf galaxies, since the AGN should be a bit brighter than typical luminous blue variable or Wolf-Rayet stars. And in general, the damped random walk also does help weed out some of that. But the sample as a whole does not have any suspect spectral features that would make me think that Wolf-Rayet or LBVs were an issue, except for the one object I mentioned where we were able to do some follow-up and determine that it does seem like a long-lived supernova, but that was a very strange object.
All right, next question we have from Angelo Riccardi, who says, hi Vivienne, very exciting stuff. Did you notice any offset AGN?
Hey Angelo, nice to chat with you. So because I was only searching at the position of the nucleus of the galaxy as defined by the NASA Sloan Atlas, the search that I carried out wasn't necessarily tuned in a way to detect offset AGN. But obviously there's been a lot of really exciting work lately on offset AGN in dwarf galaxies. So it'd be great to redo some of this in a way that's more sensitive to that. So I will say that I showed that one example where it does look kind of offset, and that's because that is the center as defined by Sloan. So we might have a few of those. And then also, I think given the pixel scale of the imaging that I've been using so far, it might be hard to even be sensitive to that. So that might be a question left to higher spatial resolution repeat imaging surveys.
And one more question we have now from Martin Elvis. Did you find any trend of variability amplitude with galaxy and so maybe black hole mass?
Great question. I don't remember if I made that plot, which I definitely should. I would say that there probably is a trend between variability amplitude and galaxy mass, with higher variability amplitude for higher mass galaxies. But I should go back and look at that again.
All right, any other questions? Again, you can raise your hand or put it in the chat. Okay, if there are no other questions, we can wrap up. Vivienne still has some slots on her schedule to meet today. If you'd like to talk with her more, and if you'd like to speak with Lauranne, please email her. So yeah, thank you both for a wonderful talk. Thanks everyone for attending, and we'll see you next time.